Welcome to The Explainer. Today, we're diving right into the foundational logic of how data actually navigates the internet. We'll be exploring the core decision-making processes of network routers, specifically focusing on the great divide between static and dynamic routing. It is a fascinating look at the ultimate balancing act, manual control versus automated scale. Here's our roadmap for today. We'll hit the basics of IP routing, explore static routes, weigh their pros and cons, unleash the power of dynamic routing, and finally, look at implementing default routes.
All right, kicking things off with Section 1, Basics of IP Routing.
Before any of that advanced routing magic can happen, a router has to check its internal map, the routing table. This table contains the directly connected networks, which are absolutely essential if you want to access remote networks. Whenever a packet arrives, the router consults this table to make its forwarding decisions. It really all starts with that foundational knowledge of exactly where these networks live.
So looking at how we actually populate that routing table, you've basically got two primary flavors. On one side, we have the static route, and on the other, the dynamic route. This, right here, is the absolute crux of network management: manual entry versus automated protocols.
To distill this down to a simple rule of thumb for this explainer, static means a human does the work by hand. You, as the network admin, explicitly tell the router where to go. Dynamic? Well, that means the software takes the wheel. Routing protocols actively communicate with neighbor routers to automatically adjust whenever there's a topology or traffic change.
Moving right along to Section 2, Exploring Static Routes.
If you're staring at a Cisco iOS terminal, this is the exact command line syntax you'd use to manually punch in a static route. You jump into global configuration mode and type out this string. Now, I know looking at raw code can feel a bit dry, so let's break down what each piece of this command actually tells the router to do. Every single piece of this string is absolutely crucial to tell the router where that packet is going. You start with IP route, define your remote destination network, drop in the subnet mask, and cap it off with the next hop address. That next hop? That's just the IP of the specific neighbor router that gets the packet next. Oh, and here's a quick pro tip from the source material. Make sure you can actually ping that next hop interface before you add the route, or it's simply not going to work. Now here's a metric you absolutely need to keep in mind: administrative distance, or AD. Think of AD as a reliability score. When a router has a bunch of different paths to the exact same destination, it trusts the route with the lowest AD. By default, static routes pointing to a next hop IP address have an administrative distance of exactly 1. That is highly trusted. But it gets even better. If you configure that static route to point directly to an exit interface, like a point-to-point WAN link, instead of a next hop IP, that administrative distance drops all the way to 0. That's the exact same reliability score as a directly connected network. You're basically telling the router, trust this path unconditionally.
Which brings us to Section 3, Static Routing Pros and Cons.
So, you might be wondering, if static routes are this straightforward and highly trusted, why aren't we just using them for absolutely everything? Well, in small static networks or in highly controlled lab environments, they actually are fantastic. They put zero overhead on the router's CPU, they don't chew up precious bandwidth chatting with other routers, and they are incredibly secure. I mean, the data only goes exactly where you, the admin, explicitly tell it to go.
But here's the catch, and it's a big one. Static routing demands that you perfectly understand your entire internet work topology. If you add just one new network, or heaven forbid a link goes down, you have to log in and manually update that route on every single router. In a growing, shifting enterprise environment, that becomes an unscalable nightmare.
And that scaling problem perfectly tees up Section 4, the power of dynamic routing. Just take a look at this setup. Even with a relatively simple 4-router topology, you're manually configuring a ton of routes just to get full connectivity. Now, imagine scaling this up to 40 routers, or 400. You can instantly see how manually typing every single path wouldn't just fail to account for link drops, it would turn into a full-time job heavily prone to human error. To fix that massive scalability problem, dynamic routing protocols step in to do the heavy lifting. We're talking protocols like OSPF, EIGRP, and RIP. They basically give routers a set of rules for how to talk to their neighbors. They automatically discover new networks, they instantly recalculate paths if a link drops, and they continuously update the routing tables across the whole enterprise, all without you having to type a thing. Finally, let's wrap things up with Section 5, Implementing Default Routes.
Now, default routes are your ultimate safety net. They keep your data from just falling into a black hole. We typically use them on what we call stub networks, which are networks with only a single exit port. Because there's literally only one way out, you don't need to waste router CPU or memory running a full dynamic routing protocol. You just point everything toward the exit door.
This specific command right here, utilizing all zeros for the destination and all zeros for the mask, acts as your catch-all. If a router receives a packet for a destination that doesn't match anything else in its routing table, instead of just dropping it on the floor, it forwards it right to this default gateway.
The really crucial takeaway here is how the router prioritizes its choices. It will always look for the longest, most specific match of the destination IP first. It wants the absolute best, most exact path. But if that highly specific search fails, the default route steps in to ensure that unknown traffic still gets a fighting chance to reach the broader internet. Just be super careful not to accidentally create a routing loop by pointing two default routes at each other. So considering the intense manual effort of static routing versus the incredible automated scale of dynamic protocols, how do you think massive modern cloud networks blend these two concepts to keep the global internet running seamlessly? It really is a fascinating balancing act of granular manual control for absolute security, paired with dynamic automation for massive scale. I hope this explainer gave you the foundational knowledge to understand what's happening under the hood of your network, and maybe even sparked your curiosity to start tackling those advanced networking questions yourself.